In Program 1 of this series, the basic principles of lubrication, the functions of lubricants and their main components were discussed in general terms. From this basic look at lubricants, the most significant rule in marine lubrication has emerged. With so many different lubricants used on board ship, designed for particular applications, great care must be taken not to mix lubricants or use the wrong type for a given application. Serious damage can occur if this rule is disregarded. This program deals with specific lubrication areas in slow-speed crosshead engines and in medium-speed trunk piston engines to promote good operational practices and to help achieve the best results from the lubricants used. Good operational practices concentrate on the choice of lubricants for each application, the selection of optimum feed rate for cylinder lubrication, and the cleaning and testing of the lubricants during their operational life. The lubrication of a slow-speed crosshead engine involves three distinctly different areas. A. Circulating system lubrication, which takes care of the bearings and moving parts in the crankcase. B. Cylinder lubrication system, which takes care of the lubrication between the liner and the piston rings. And C. The lubrication of turbochargers, hydraulic governors, hydraulic exhaust valve actuators, and the turning gear. All of these may use different lubricants. The circulating system oil is there to lubricate the moving parts of the running gear and provide the drive for the control system. Typically, this would be an oil of viscosity grade SAE 30, having a viscosity index of between 80 and 100 and a low TBN number. The oil should resist foam formation and possess good water separation characteristics. The engine manufacturer's manual will contain recommended lubricants. Besides lubrication, the lubricant will transport contaminants and metal particles as it circulates, which then need to be removed. This is best achieved in a centrifugal separator, working in bypass, drawing oil from the oil drain tank and returning it there after cleaning. The application of inline filters also helps to remove some of the contaminants. The ingress of water into the system is always a danger, and frequent checks should be carried out on the system oil to ensure an early detection and removal of water. This is most important, as the presence of water increases the risk of corrosion as well as microbial contamination of the oil. The water must be kept out or removed totally as quickly as possible from any system oil. Again, systematic centrifugal cleaning will lower these risks. Typical sources of contamination may be leakage from the cooling system and from the centrifuge sealing water if not operated correctly. The cylinder lubricating system uses a different type of lubricant, as the job it is required to perform differs from that of the system oil. The cylinder lubricant must be of a higher viscosity so that it can form a good lubricating film between the liner and the piston rings. It must also withstand the heat variations in the combustion area and must deal with the combustion products. Under normal running conditions, an alkaline cylinder lubricating oil of SAE 50 viscosity is used. The alkalinity or TBN value of the oil is related to the sulfur content of the fuel used. Typical values may be for sulfur content of 0.5 to 1%, between 20 to 25 TBN. For higher sulfur content over 2%, the TBN number may be 70 or higher. Once the correct cylinder oil is chosen, the correct feed rate must be established in accordance with the engine builder's recommendations. The feed rate has a critical effect on good engine operation, apart from the question of oil consumption. With too low a feed rate, the danger of the oil film breaking down, causing undue wear, is much increased. The correct feed rate will allow the formation of the lubricating film between the liner and the rings, and will reduce the effect of its breakdown at piston reversal points. The use of heavy fuel oil with high sulfur content is making the job of the cylinder lubricant very difficult. Even high alkalinity oils cannot hope to neutralize all the sulfuric acids which are produced during combustion. The cooling system must be operated so that the cylinder liner temperature is not dropped below the temperature at which the sulfuric acid may condense out on it. Acid condensation depends on the engine combustion pressure, the liner temperature, the concentration of the sulfur oxides, and the humidity of the intake air. The engineer must ensure that the moisture content of the intake air is meticulously controlled, and that the temperature of the cylinder liner is kept high enough to prevent acid condensation. The way an engine has been run in after commissioning or an overhaul is critical to establishing good cylinder lubrication. A good run-in procedure will create a good wear-in of the cylinder liner and piston ring. A good seal is obtained between them where a thin oil film provides reliable and effective lubrication. To achieve this running-in performance, a running-in cylinder oil may be used. The period of running in should be decided upon in accordance with the engine manufacturer's recommendation. Even if only new rings have been fitted, the running-in procedures should be as near as possible to that recommended for new engines. During the running-in period of a new engine, the feed rate should be high. After running in, the feed rate is gradually adjusted until the recommended feed rate is reached. The use of the correct lubricant and the correct feed rate for the engine load will help to achieve the best result from a cylinder lubricant. The lubrication of ancillary equipment of the main engine will be discussed in Program 3. Due to vital design differences, in the case of medium-speed diesel engines, the cylinders are open to the crankcase. This means that the crankcase oil can be contaminated by corrosive combustion products. The chosen system oil must deal with these contaminants as it lubricates the system. The lubricant must also maintain effective lubrication under high mechanical and thermal loads, and must transport solids from the cylinder to the cleaning devices, such as filters and centrifuges. It must withstand heat as it fights corrosion and wear. In doing this, it must resist oxidation and thermal breakdown, and must keep the engine clean. Some medium-speed engines, in addition to high load factors, introduce new problem areas for the lubricant to deal with, such as piston undercrown deposits, ring zone fouling, and cylinder bore polishing. So the lubricant must also have increased dispersancy, detergency, higher oxidation, and thermal stability. It must also have higher load carrying capacity to avoid scuffing problems of cams and rollers. The aim is to maintain effective lubrication at all times throughout the machinery. Inside the cylinder, the thermal and mechanical stresses on the oil film peak due to combustion while the piston speed is 0. The oil film can break down easily, and the best the engineer can hope for is sufficiently effective boundary lubrication at this point. In medium-speed engines, the circulating system oil is also providing cylinder lubrication and piston cooling, and the breakdown of the lubricating film between the liner and the piston rings tends to cause blow-by, which results in further contamination, including unburned fuel. Unburned fuel contamination tends to reduce viscosity, leading to less effective lubrication. The main source of fuel contamination is a leaking fuel injector. A typical lubricant which will successfully lubricate the entire engine is an SAE 40. The oil will generally be designed with additional alkalinity, detergency, dispersancy, with antioxidant and EP additives. In all cases, the engine manufacturer's recommendations should be strictly adhered to. Some medium-speed engine designs use a separate cylinder lubricant, but in almost all cases, the system oil is used for cylinder lubrication. Lubricant care is a critical factor in good machine operation. The conditions of storage on board, prevention of contamination by water and hard particles during storage, the cleanliness of the machines when charging them with lubricants, and the continuous filtering and cleaning of the lubricants during use are equally important phases of looking after them. There are many filter types used on board ships, and their periodic cleaning and monitoring according to manufacturers' recommendations is essential. Medium-speed installations use back-flushing or self-cleaning filters. Pressure differential between inlet and outlet triggers off back-flushing. If difficulties arise with this type of filter, for instance, frequent back-flushing, the filter elements should be dipped into chemical cleaners which are capable of dissolving and removing hard calcium compound deposits. Or an ultrasonic bath may be used for cleaning them. Filtering the lubricants will only remove some of the contaminants, usually the larger hard particles. The lubricants need further cleaning, and the use of purifiers for this work is common practice. These will remove particles as small as 0.5 microns and remove most of the water content. Increased use of lubricant condition monitoring and wear metal particle analysis greatly reduces operating costs, as the resultant trend analysis usually highlights impending problem areas before breakdown occurs. The savings come not just from avoiding unexpected breakdowns and their consequential costs, but from being able to eliminate problem areas before they contaminate the lubricant, forcing its untimely replacement. The combination of wear and contaminant elements usually points to specific developing problems from which practical recommendations can be built up, reducing the need to open up the machinery for inspection or discarding lubricants before their time. The main items which are checked during analysis are flash point, viscosity, water content, alkalinity, and metal wear particles. The resultant values are then compared with those of the new oil to detect major changes. For the oil analysis to be effective, the job must be done using good representative samples taken preferably after the pump, strainer, cooler chain, before the oil re-enters the engine. In any case, the samples for trend analysis should always be taken from the same point in the system. The method of taking the sample, as well as the utensils used, must be such that contamination of the sample is avoided. In the laboratory, the lubricants will be examined for the presence of combustion contaminants, as well as for metal debris against established control values. Increasing trends and their combinations will allow the required remedial measures to be formulated. Modern lubricating oils, when carefully monitored and maintained in good condition by the engineer, can have an almost infinite life. Even if this optimum is not always achieved, extended oil change intervals will reduce used oil disposal problems with significant cost and environmental benefits.